Hello everyone, this is Luboš Pirkl from CFD Support. Welcome to the webinar about the optimization of a radial pump using Xtreme, CFTurbo and TCFD. In today's webinar, we would like to share with you a smart engineering workflow where the radial pump is designed in CFTurbo, simulated in TCFD, and all this is run in an optimization loop using Xtreme software. I hope everything works well. We are running live, so in case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. The webinar is being recorded and the recording will be made publicly available. In the end of the webinar, there will be a Q&A session dedicated to your questions and our answers, so feel free to ask your questions anytime during the webinar. You can find the question form in the GoToWebinar menu. And yeah, it will be our pleasure to answer all your questions. And I think this would be it for the first slide, for the beginning. Right in the beginning, I would like to stress out that this is a freeway webinar of 3 independent companies: Optimal Computing, CFTurbo, and CFD Support, with 3 independent standalone software tools: Xtreme, CFTurbo, and TCFD. So, okay, so the projects are independent each other, and yeah, I'll continue with introducing the webinar speakers. So together with us on the line, there is Stefan Pierret from Optimal Computing. Hello, Stefan.
Good morning, Luboš.
Hello.
Sorry, good afternoon. Yes.
Yeah, sure. And yeah, so how are you? Are you ready for the webinar?
Yes, sure. We are well prepared. So I hope we will show interesting topics for the attendance.
Okay, great. So I only note that Stefan is the founder of Optimal Computing and he's also an executive manager. And in today's webinar, he will introduce us into their optimization tool called Xtreme. And there is also Oliver Felde with us. Hello, Oliver.
Hello, Luboš. How are you?
I'm fine, thank you. So again, the same question. Are you ready for the webinar?
Yes, I'm ready and well prepared as Stefan, and I'm looking forward to have this webinar together with you again.
Okay, it's perfect. So, okay. So I just note that Oliver is a senior scientist and developer at CFTurbo, and he will present the CFTurbo part of this webinar. And finally, yeah, this is me, and I'm happy to work at CFD Support and to tell the world about simulations and what we do here. Yeah, so this is us. Here's the agenda of today's webinar. The webinar is going to take about an hour. After a brief introduction, which is happening right now, we will start. There will be a few parts. In the third part, Oliver will tell us about CFTurbo and introduce us the important aspects of CFTurbo. Then in the second part, I will give an introduction to TCFD and tell you a little bit about what we do here at CFD Support. And in the third part, Stefan will introduce us to Optimal Computing Company and their product Xtreme, and he will also tell us about the project, which is the topic of this webinar, which is called the optimization of a radial pump using Xtreme, CFTurbo, and TCFD. And finally, in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to ask your questions, ask them anytime during the webinar. Some questions will be answered right away in the webinar, and the rest of the questions will be answered later via email. So you can be sure that all the questions will be answered. Okay, so I think we can start with the showing the stuff we have. So Oliver, may I ask you for your part?
Sure, you can. Yes, before I start with a very brief introduction into CFTurbo, I just want to give some information about our company. Our main product has got the same name as our software, as the company, and CFTurbo is a modern and powerful and user-friendly tool for the conceptual turbomachinery design based on latest design theory. Lubos, can you? Okay, right now we have a bunch of active clients worldwide, around 200. We have implemented a couple of modules to design special turbo machines. So maybe the most important one is the module for pumps, both centrifugal as well as axial. Then we have modules for fans and blowers, again, both centrifugal and axial. Compressors and turbines can be designed, and of course also other components within complete stages like stators that might be vaneless or might have vanes. And finally, of course, it's important to have also a module to design the volutes for centrifugal turbo machines. And the industries we serve are aerospace, automotive, consumer products, energy, oil, gas, marine, mechanical, and process engineering, and even semiconductor industry. Okay, so that's quite quickly about CFTurbo. And
okay, so maybe it's time to make you the presenter, right?
Right. Let's see whether.
Yep. So.
I do. Oh, I want to.
Yeah, I think it takes.
Choose the correct.
Yes, we can see your screen now.
Okay.
We can see it.
Okay, because today's topic is not the conceptual design and the maybe the analysis in a CFD tool only, but also the automatic optimization. I don't want to spend too much time to introduce you with the capabilities of CFTurbo. That's why I opened an already designed pump stage, which Stefan later on will use in the optimization workflow. But nevertheless, I want to give some information about the basic of the design with CFTurbo. The central entry into the design is always the definition of the global setup of an operating point. And here it's just the flow, the head, and the speed the pump should run on. What is also important is to know the correct material properties, because they are used, at least the density is used in the design process, but other attributes or properties like viscosity and so on are used to export information to a CFD interface. Okay, what we do in CFTurbo and what is the big difference to general purpose cut package is that we make a conceptual design. So we try to make as good proposals for the dimensioning, for instance, for the blading and so on, based on that operating point, based on the solution of balance equations like continuity equation, first law of thermodynamics, Euler equation of turbomachinery, and so on, and also a lot of empirical data that we have collected and implemented. So here right now you see, for instance, that on the basis of that operating point, we not only calculate the specific speed, which is one of the most important numbers in the turbomachinery design theory, but also we make proposals for a decent meridional contour, which which is based on that specific speed number, for instance. Okay, once that is defined, one can add components to the projects that might be part of the stage. So of course here it's a single stage machine where the most important component would be the radial impeller, and that's why I want just to go quickly through some examples of the design steps. So there's the main dimension where the impeller diameter, the impeller outlet width, and the impeller inlet diameters can be set up. And as I said earlier, we make use of empirical data, like for instance the work coefficient that comes from the Cordier diagram. This time we use the reference of Johann Gülich's textbook. And if one presses the calculate button, there are some proposals based on these empirical data and based on the balance equation I just mentioned. But at any time, people can override this stuff and can adjust the model in accordance to its respective needs. What is very important for the optimization is that everything is parametric. So for instance, if I jump quickly to what we call the blade properties, where we define blade angles at leading and trailing edge. Again, we can make proposals by using that calculate options, but we also can override these values here. So for instance, if I want to increase the pressure a bit, so I could change the blade angles at the trailing edge a bit. And if I now press OK, go to the 3D model, then immediately I get an updated geometry, and this again could now be used for further analysis or even an optimization. And this all not only can be done interactively, it can also be done on a command line in a batch mode. And what we have prepared for this batch mode run is something what we call the batch mode optimization dialog. So in that dialog, one can not only tell which parameter of the stage or of the pump this time should be changed in a batch run, but also export actions can be defined. So as an example, I just want to change, for instance, the number of blades and maybe the trailing edge angles, as I already did. And afterwards, I want to investigate the new geometry with the help of a CFD package. And this time, of course, it should be TCFD. Then the only thing I have to do is to tell which components should be considered, where's the directory, and have to tell a couple of settings. I leave it to course for the triangulation just to save a bit of time. And then I can add this to the export actions and can save this as a special file with that special extension here. And let me change to the location where this batch file has been saved to. If I open this and change the parameters here that are prepared for the batch run, so maybe changing number of blades to 6 and changing the blade angles, make them a bit smaller so that we can see there has been a change done later on. And if I save that, I can start to make that batch run, and I have prepared that in a batch file, which I just want to show you. And it's simply, I can run CFTurbo from command line in a batch mode, and as an attribute, this CFD batch file is given. And if I do that, just by running it, CFTurbo is started in batch. It opens the reference file, loads the CFD batch file, and it's going to take the changes, doing the exports. You can see now the resources file directory has been created, and also the modified CFTurbo file is created. And after a couple of seconds, also the control file for TCFD is created, and then one could start the CFD for it. And yeah, putting all together is just the precondition to have CFTurbo implemented into an automatic optimization flow. And this is then going to be Stefan's part, and that's why I don't want to tell anymore. You see here, because of the course triangulation, it's already done, and everything needed for TCFD is well prepared. So for instance, the new geometry, and maybe the last thing I can show is I can load this modified CFD file in order to check whether the parameters really have been changed. Okay, so number of blades is now 6, and also the blade angles have been adjusted, and that tells you that this change was successful. Okay, saying that, I'm finished, and I would like to give back the presentator to Lubos.
Okay, thank you, Oliver, for your part for the presentation. It's very nice to see how CFTurbo can be handled in the batch mode. So I'll take back the presentation. So I hope soon you will be able to see my screen. So tell me when you see it. You should see.
Not yet.
Okay, the presentation where we ended before we hand it over to you. So so can you see my screen or not yet?
Not yet.
Okay.
Not yet. Not the presentation.
Okay. The GoToWebinar client.
Yes. It's there.
No, you can. Okay. So I'll. Okay. So there will be CFD support, the simulation part. So I will introduce you just very quickly to general information to our company. So yeah. So CFD Support is a worldwide operating company which develops engineering simulation software to be used by engineers and designers for a large variety of fluid engineering applications in turbo machinery, energy, automotive, or marine sectors. Last year we celebrated 10 years of our existence. Our headquarters is located in Prague, Czech Republic, and yeah, let's say our field is definitely engineering simulations. We primarily focus on development of CFD software with very high added value for CFD users. It's definitely a high-end software for CFD professionals who know what they want. We are obsessed with accuracy. Accuracy is of our highest interest. And besides accuracy, we are focused on automation, repeatability, and application-tailored simulations. We don't believe in general purpose codes. We don't believe that a particular CFD software can accurately simulate everything, or that anyone can simulate anything. We do believe that any successful CFD project is a result of focus, skills, experience, patience, and dedication. CFD support was originally founded as a consultancy business for OpenFOAM, but a few years into the consultancy business, we felt that our clients deserve something more. So we decided to launch a new project, a software product, a CFD code called TCFD. We have put all our skills and experience and our passion into it, and today our mission is developing simulation software with the best value cost ratio in the whole market. We believe in open source. We have invested more than 30 many years of focused team development on top of OpenFOAM and other open source tools, and that's why we are being picked. So TCFD is a comprehensive CFD workflow which successfully merged the benefits of open source with the benefits of commercial codes. Due to the open source nature, it's unlimited and extremely flexible, and due to the commercial code nature, TCFD has a graphical interface, professional technical support, it's robust, it's accurate, it's automated, it's well tested, and it's ready for the use in the industry. So this is how the graphical interface of TCFD looks like. The user can do everything here, from the simulation setup to the simulation run to the detailed post-processing of the results. And besides graphical interface, the batch mode is available, of course, and TCFD can be run by another software like in this project. Okay, about the main applications, TCFD core business has always been turbo machinery simulations, for example, pumps. TCFD can simulate many kinds of pumps, many kinds of machines, all sizes, both radial and axial types. Also fans and blowers, both compressible and incompressible fluid flows. Also, one of our best is hydro turbines and compressors and turbochargers, as well as wind turbines. Later, what had worked so well in turbo machinery field, we decided to extend for the external aerodynamics to simulate, for example, cars or car bodies or the aircraft. And nowadays, TCFD also simulates internal aerodynamics, for example, valves or hydraulic valves or various manifolds and intake manifolds or exhaust manifolds and piping systems. TCFD shows fantastic performance for simulating marine propellers or ship hydrodynamics, also the air propellers and various wind loads acting on the surfaces of the objects. And from the last year, TCFD is also capable to simulate flows with including heat transfer and the human comfort. So yeah, normally I show here some project examples we did, some benchmarks, but I guess we have a lot to show you later in this webinar on the study we have on the radial pump. So I will just say very little about our future plans, because we believe that we can contribute even much more to the simulation environment. Later we want to introduce a new simulation environment called TCFD. It will be a smart connection of many open source projects to deliver a single comprehensive engineering workflow. TCAE is the name of the new project. It will include several independent modules like verticals. Each of them will be like standalone plugin, and all of them will be automated in the smooth process. And there will be structural analysis, CFD, and of course fluid structure interaction, and the process will be much more complex and much more comprehensive than it used to be in the past. Okay, I'm not gonna go too much into the details. TCFD or TCAE now, it will still keep its modularity as it was with TCFD, and it will be able to be used inside any other existing workflow. And regarding this, we have like two ways of thinking. It's the horizontal one where we'll be adding new plugins and new capabilities, and the vertical one where we'll be adding new high-tech methods and making the product better in vertical sense. Okay, so I think maybe this would be it from me. So maybe I was a little bit quicker than I expected in the first place, but now I would like to ask Stefan. So Stefan, are you ready for your part?
Yes. Thank you very much. Yes.
Okay, so I guess it's time to hand over the presentation over to you. So I'm right now making you the presenter. So
Okay.
let's see how quickly it happens. Yes, we can see your screen now. So
okay.
you can start. Yes.
Okay, and you see the presentation. Yeah. Okay.
Yes, we can see it.
And okay. It's okay. Okay. So good afternoon to everybody. So I have two presentations, two different presentations. The first one is presenting the company itself. So Optimal Computing, I cannot. Okay, so Optimal Computing is a small company based in Belgium, created in 2008. And we do, let's say, three different things. We do numerical optimization, as this will be the focus of this presentation. But we also work on artificial intelligence, and we also developed bespoke software for customer in different languages. So focusing on the topic of today, I have this flow chart where you see a typical optimization process, and this is the optimization process that we will be presenting today, involving parametric modeling using CFTurbo, using CFD, using TCFD, which is based, as you see, on OpenFOAM, and then to add to this simulation some mechanical calculation based on the open source code Calculix. And to perform this calculation, we need a mesh, and the mesh is created using also an open source software that is called NetGen. And once we have this simulation environments, these environments get as inputs or needs as inputs the design variable, and as Oliver showed you, it can easily be read by CFTurbo using the batch file. And here we define as many design variables as we want, and the simulation is processed automatically here, and we automated everything using Python scripts. And at the end, we get some response variables such as the efficiency, the head, or the maximum von Mises hysteresis, or the vibration modes. And then we connect this simulation package or this simulation suite with our optimizer Xtreme. Xtreme, how does it work? It's based, as I said, on some artificial intelligence technique like artificial neural network and genetic algorithm. But to do that, first we build what is called a design of experiments, meaning that we create somehow randomly, some designs, some pumps in this case. And when we have those pumps, we can launch the simulation using the simulation chain I showed you. And then when the simulations are finished, the results, the most important results, are stored in a database. And we store typically the design variable and the response variable. When we have this database, then we can use a neural network, and we can train a neural network that will learn the relation between the design variable and the response variable. And the advantage of having this is that we can evaluate many many different a set of design variables in a few milliseconds using the neural network instead of a few hours with the complete and accurate simulation tool. But this allows us to have an approximate response and to use genetic algorithm in order to find an optimal solution based on the prediction of the neural network. This is what we call the inner optimization loop. And when we finished with the genetic algorithm, we are able to provide to the accurate simulator the task to evaluate the accurate response. Then we store the results into the database, and then we can go on with another loop here. And this we proceed in the same way, except that after one more simulation, we have one more sample in the database, and therefore the system is improving iteratively like this. And we have a kind of learning process with three key elements: a database, a neural network, and a genetic algorithm, which is there to find the optimum and to push the learning process. How does it work graphically? Let's take a very simple problem with one design variable and one objective that we want to minimize. Then we will first evaluate randomly a number of points like this. When we have enough points using the design of experiments, we can build an approximate model using the neural network, and we have this relation. Then we use a genetic algorithm to search for the optimal value. And when we have the proposed optimal value, we use the accurate simulator in order to find the accurate answer, which might be this one. And then we do again and again the same cycle by constructing the approximate model, searching for the optimum using the genetic algorithm based on the neural network approximation, and then evaluating the accurate answer using the accurate simulator. Okay, so this is the process the process that is implemented into our software Xtreme. And with this process, it's called a black box optimizer. It means that there is no need to have access to the source code of the simulation tool, and it has a number of advantages. And one of the advantages is that it can be applied to any domain, any physics. It can be aeronautics, automotive, buildings, finance, manufacturing, space, structural mechanics. So it can involve fluid, structural mechanics, thermal simulation, acoustic simulation, or anything. Our product Xtreme is declined into three different packages. The first one is a full graphical user interface that is very easy to use. A second packaging is inside Excel. It's available in a plugin inside Excel. And the third packaging is in a programming language using an API in C++, C, or Python. The advantage of this third package is that it can be included and it was included in one commercial software, simulation software, and a customer decided to include our optimization package into their commercial packages. So in terms of performance of the optimization, I have these slides where, and maybe I will concentrate on this one. It's a function which is called the Rosenbrock function, which has the characteristic of having a very narrow valley here, and it's not easy for all optimizer to efficiently find the true optimum of this function. And on this graph, you see the performance of a simple genetic algorithm, which may require many thousand evaluation. And when we use our numerical optimization algorithm, the convergence here is much, much faster. On the left, it's a problem where you have one local minimum and one global minimum. And here we take the advantage of using genetic algorithm, and the optimizer is always capable to find the true global objective function in a much faster way than what a genetic algorithm can do. Okay, and typically what we see from our experience is that our algorithm that we call the FastGA is between 10 and 40 or even 50 times faster than a classical genetic algorithm. Another test function is this one, where you see it's full of bump and local minimum. And again, you see the performance using a genetic algorithm in terms of number of function evaluation. And if you use the FastGA, it's very quick to go directly to the true optimum. And typically, again, the same ratio between 10 and 25 times faster than a traditional genetic algorithm. What are the key advantages of the software or the algorithm is that it's a black box optimizer, meaning that we don't need to have access to the internal source code of any simulation tool. It's very fast to converge, so we are able to deal with simulation that takes quite some time and typically equal to 1 hour or more. It can deal with noisy functions. It can deal with multimodal functions, meaning that cases where you have function with both local and global minimum. It can deal with uncomputable function, meaning that if you launch a simulation and this simulation does not converge or crashes for any reason, the optimizer is capable to take this information and continue. It can deal, as you will see later in this case, it can deal with many objectives, many constraints, and also what we call interval constraints, for example, for vibration modes. We can do parallel optimization. We can use continuous or discrete design variables. It could be the number of blades, could be a design variables. And we can deal also with, it's a different algorithm, but it's for sequence optimization, as I will show you in the next slides. In terms of performance, again, we have a large test database containing about 50 different test cases, which are well-known and hard optimization and hard to optimize functions. And on average, we see that the ratio between the convergence of a genetic algorithm and our fast genetic algorithm is of the order of 25. This is also another application using sequence optimization, where we optimize, this is the case of a structure that is welded here, and those beams are welded on a plate. And in this case, there are 54 different welds to weld the complete structure. And due to thermal effects, the final structure is deformed. So the question is, in which sequence shall I weld the different beams in order to minimize the maximum deformation of the structure? And we have an algorithm for that. And you see on the left the deformation of the original welding sequence. And here on the right, the deformation of the structure based on an optimized welding sequence. And for this case, we have reduced by 60% the displacement at the end of the welding process from the original sequence until the optimized sequence. So to conclude this part, I think I showed you that we have a unique optimizer, unique in terms of performance. It can be applied to complex optimization application. It can deal with uncomputable function, with constraints that are difficult to deal with. It has the possibility to make optimization in parallel, to make multi-objective optimization. It's an optimizer which is very robust because very well tested on various cases and various functions. It can deal with continuous and integer design variables and also with sequence optimization. As I showed you, it's a self-learning method. And in our company, we have a large experience in complex engineering optimization. And we are used to use this software in consulting mode projects. Okay, that's it for the first part of the presentation. Shall I go to the second one, Luboš?
Yes, please. Yeah, we follow it.
Yeah.
It's very interesting so far. So please go ahead.
Okay. Okay, in this presentation, I will focus. I think I have about 10 more slides. I will focus on the project we did, thanks to the collaboration with CFTurbo and CFD support. My presentation is split it in different parts. First, the first slide with the motivation. Then I will quickly present the softwares that we used. Then I will present the parameterization of the geometry using CFTurbo. And then I will show you the optimization workflow objectives, then the optimization results and some conclusions. So why this project? It's because we wanted to show how that it is possible to set up such a quite complex optimization application in only with little effort. And for that, we concentrated on a pump, and we decided to include the hydrodynamic optimization together with some structural mechanic constraints and objectives. And for that, we use our highly efficient optimizer. We used CFTurbo, TCFD, and all the software I already showed you in the previous presentation. So we have CFTurbo, TCFD, NetGen and Calculix for the mechanical parts, Xtreme for the optimization, and all those software are, let's say, coupled together using some Python scripting. So for the first software, CFTurbo, as Oliver showed you, it's very easy to use, and it's the most important things for the optimizer is to be able to launch it in batch mode, as Oliver showed you. And in this case, we decided about to use 13 parameters here. They are listed here. So you have the position of the leading edge at hub and shroud here on the meridional plane. You have the 4 thicknesses at leading edge, trailing edge at the hub, leading edge, trailing edge at the shroud. You have the circumferential position of the trailing edge at hub, the leading edge at shroud, the circumferential position of the trailing edge shroud, and also the blade angle, which are the 4 angle at 2 at the leading edge hub and shroud and 2 at the trailing edge hub and shroud. And here you see the initial value and the variation range. The number of blade was kept constant for this case, although it could be a design variable. And we decided to keep the main dimension constant. For the fluid simulation, we used TCFD, which is also very well suited for this application because it's an accurate software, it's it's converging fast, it's robust, and it can be launched in a batch mode. So for this case, we use a steady simulation of a pump and a volute. The mesh, the CFD mesh, has more than 1 million cells, and it runs in 21 minutes on a normal desktop equipped with 6 cores. The fluid is water. The rotational speed is this speed, 1,770 RPM. The flow rate and the head of the pump is 33 meter. This is the convergence of the CFD calculation, and this is the history of the residual. So we converge. We decided to use 500 iteration to get a converged solution. For the mechanical simulation, as I said during the presentation, we use NetGen to generate the mesh and Calculix to calculate both the static and dynamic mechanical properties. We had to, let's say, NetGen is available in source code, so we could get the source, recompile in order to be able to launch it in batch mode and have all the freedom to manage the meshing parameters here. We used a pump made in PVC with this density, this Young modulus and elastic limit, and the mechanical mesh has more than 400,000 elements. We used first order elements. And here you can see the second vibration mode, for example, and the fifth vibration mode calculated by Calculix. Here you see a cut of the mesh, of the wheel and the mesh. And here you have an idea of the mesh that we use for the mechanical calculation. Now, Xtreme, as I said, Xtreme needs a simulator, which in this case is composed of CFTurbo, TCFD, and Calculix. And we plug Xtreme here to manage to drive the optimization process. Okay, this is the interface of the software. And in particular, this is, I will come to that later. This is how you can represent the response between some design variable and some objectives. For the optimization, we decided to optimize and therefore maximize the hydraulic efficiency while putting some constraints on the von Mises stress on the wheel. We also decided to add constraints on the vibration modes, and I think it's a key point in the application we addressed here. It's to show how all those tools together and Xtremes are capable to optimize also with the vibration modes. And we we specified a number of frequencies that are forbidden. For example, the vibration frequency around the rotational frequency is of course forbidden to avoid to break the wheel, and also all the multiples times 2, 3, 4, 5. 7 is because there are 7 blades, so we also forbid this frequency, vibration frequency, and also 2 times the number of blades. And around those forbidden frequency, we said, okay, the vibration modes cannot fall into those limits. Now, then we decided to launch the optimization of this application, and we started by generating a design of experiments with 20 design, and therefore 20 pumps that were simulated using CFTurbo, TCFD, and Calculix, and it took about 20 hours, about 1 hour per simulation to reach these points here. And then the optimization starts here for 60 more iterations. The blue curve here is the efficiency, the hydraulic efficiency. So we see that it's quickly go up, and then we converge rapidly to a value that is 2.2% more than the original pump. And the red curve here is the maximum von Mises stress on which we put the constraints, and we see the evolution of the von Mises stress. And on the right graph, I think it's a very important aspect of this optimization. We represent the eigenfrequencies. In blue here and red, we have the first and second vibration modes. In blue, we have the third vibration modes. Here we have the fourth, and in blue here we have the fifth vibration modes. And with the dashed zone here, you have the vibration zones that are forbidden for any vibration modes. Okay, and here you see the number of simulation evaluation from 0 to 80. So 20 for the DOE at the beginning, and then we start with the optimization. And we see that here we have the third vibration mode that is below the forbidden range. And for many optimization algorithms, it would be difficult to jump on the other side of the forbidden range. And here we see that the algorithm is perfectly capable to do that. And this is the same for the fourth vibration modes. We see that it's below the zone, and then at some point, the algorithm was able to jump above this forbidden range parts. So as I said, the efficiency increased by 2%, while keeping the von Mises stresses to a very acceptable level, and we see the movement of the eigenfrequencies. Here you can see the difference between, in blue, the original blades, and in green, the final blades, the optimized blade. And here you can see the value of the design variables for the thicknesses here, the relative position of the leading edge, the circumferential position of 3 key points, the blade angle, and in green you have the values that reach the lower bounds that we imposed, and in red the values of the parameters that reached the maximum value here. So almost all the design variable reach either the minimum or the lower bound or the upper bound. So if we had to restart this, we could enlarge a little bit more the bounds on the design variables to even try to catch a better improvement. In terms of calculation time, as I said, it takes about 60 minutes per simulation. And in this case, we saw that we reached the optimum after 63 simulations. So it's less than 3 days, between 2 and 3 days. And in total, we made 80 simulations. All geometry were successfully generated. 74 out of 80 CFD calculation converged. This is very good. And 6 did not converge and were automatically rejected by the process. Now, to exploit and understand the results, the Xtreme graphical user interface is capable to show the approximation obtained by the neural network. And for example, here you can see the hub, the leading edge hub thickness, the leading edge shroud thickness, and the efficiency. So you can see the logic of modifying or the consequence of modifying those two design variables on the efficiency. It's another way to represent the results. And finally, some conclusions. So you saw the successful optimization of sorry, it's not fluid. It's hydromechanical optimization using 13 design variables in less than 60 simulation runs. The whole clock time is less than 60 hours on a very, let's say, normal desktop computer. We were able to take into account the vibration frequencies, and you saw that the simulation, both the simulation and the optimization, are robust altogether. And I think it shows you a quite important optimization results. However, it could be better. It could be possible to do better by including the number of blades in this study, optimizing the hub and the shroud contours, or even the volutes, to perform unsteady simulation with the condition of probably having more computers to do that, and then also to include the interaction between the fluid and the solid to calculate the static deformation, for example, of the wheel. Okay, so that's what I wanted to show you today.
Okay, thank you, Stefan. It was very, very interesting. So thank you for your contribution, and thank you for the so much effort you made in this project. And yeah, so I'll take back the presentation. So I hope now it switches much faster than before. So tell me when you see my screen.
Not yet.
Okay, but in any case, we are moving now to the latest part of our webinar, which is the Q&A session. So I would like to ask the audience to ask your questions. Please feel free to ask your questions. As you know, there are no stupid questions. There are only stupid answers. So don't worry about your questions. Feel free to ask. We will do our best to answer at least a few of them. You can be sure that all the answers will be answered. All the questions will be answered. For example, via email or right away here. So feel free to ask. It's our pleasure to answer. Okay, so still my screen is not on.
Oh, it is
It
displayed.
is. Okay,
yes,
so
yes.
so now it was the Xtreme part, the optimization part, and now yeah, it's the Q&A. So gentlemen, please take a look. If you see some suitable question, you can answer. Maybe I can start. Rishab is asking. He has left the webinar in the meantime. But anyway, he's asking whether there is a cavitation available in TCFD. Yes, it is. Yes, it is. There are 3 modules for cavitation. There are some basic approaches, and there is also full cavitation multi-phase module in TCFD. So it's TCFD is definitely ready for dealing with cavitation. So that's for sure.
Yeah.
Well,
maybe I can take one from Christian, who asked what does Xtreme with CFD simulation that do not converge? So in fact, in the Python script, we capture whether each of the simulation run correctly, and if the CFD software reach a given level of convergence. And if it's not the case, then Xtreme will take this information and will not take this simulation as a valid simulation, and we learn that this geometry is not, let's say, feasible, because we assume that if there is a problem in a simulation software or the convergence, it's because there is a physical reason that forbids the flow to converge. So we can deal with that.
Okay, sure. Okay, so it was this.
I have another I can answer from Alberto. Is it possible to impose more than one optimization objective? Sure. So in this case, that's true that we had only one objective, but there is no problem to impose 2 objectives. And then there are 2 options. Either you sum up those 2 objectives to have a single global objective to optimize. This is one solution. Or the other solution is that inside Xtreme, there is also the Pareto front techniques that allows to make to optimize simultaneously for 2 or more objectives.
Okay, thanks. It's that. Okay, so there are some questions. Maybe I'd like to answer this one from Gabriel. It's yeah, it's the big one. What's the percentage error of TCFD with respect to laboratory tests and measurements? That's a big question, but it's a question on accuracy, which is of our highest interest. So I can show you some of studies with it. That's a big question, right? We believe that all the projects, or I would say successful projects, are, it's not a question of what code has been used. It's rather a result of the focus of skills, of experience. It's a question of patience and dedication of the actual engineer who solved the project. So I can show you, for example, this one. We used a pointwise mesh for this marine propeller. It's a well-known Potsdam propeller test case, which was measured in SVA Potsdam laboratory in Potsdam, Germany. And as you can see, the agreement with the measurement of and the TCFD results of the simulation results, it's absolutely perfect. It can't, maybe it can't even be better, because of course the measurement has its error, and such an agreement is perhaps the best what we can ever get. Maybe I can show you another one. Maybe this Ahmed body benchmark again was so good that it couldn't be even better. So, but yeah, so I suggest. I know it sounds maybe sometimes a little bit strange, but don't ask about the accuracy of the code, but ask about the engineer who did the study. So that's just a little note from my side. So yeah, so would you like to answer any other question? See a good one. Yeah, I see some other special questions. Maybe this one quickly I can answer from Ilya. What numerical method does TCFD use? Finite volume, like OpenFOAM? Yes, of course. It's the numerical solver is based on OpenFOAM, so it's finite volumes, and the solver itself is based on OpenFOAM. It's a rewritten solver to be robust. There are other, let's say, turbo machinery boundary conditions and special, let's say, limiting tools, but yeah, it's based on OpenFOAM definitely. And it's under GPL, and the source code is available, of course. So have you, do you see any other appropriate questions, or can we move in the webinar?
Well, maybe I can ask Volodimir's question. Is there any opportunity to use CFTurbo for mean-line optimization of the geometry, for example, to do an initial sizing study of the machine to choose certain key diameters and passage depth dimensions, as well as to select the desired rotational speed? Yes, of course, because as I told you earlier, everything is parametric, and even some geometric results will be given by CFTurbo itself. So the answer is yes, absolutely.
Okay. Okay, thanks. So I think it's time already. So I will move to conclusion of the webinar. Don't worry about the unanswered questions, because there will be answered via email. We have them recorded in the system. So I think it's time to conclude. So this would be it from us. So we would like to thank you for your attention. It was a pleasure for us to show you what we did and what we also are going to do. I think it's obvious that we are speaking here about 3 standalone independent tools. So I guess you understand, or I guess you get that the questions about CFTurbo are about to be sent to CFTurbo. Questions about the optimization, this Xtreme tool, are to be sent to optimal computing, and of course the questions about simulation and about TCFD are about to be sent to CFD support. And I think this would be it from me. So Stefan, would you like to say something?
Yes, so I thank you everybody, so CFTurbo and TCFD for the collaboration on that project, and also all the attendees for the questions and for attending this presentation. So thank you very much all. And if you have any question, feel free to contact us.
Okay, thanks to you. Thank you, Stefan. And Oliver, would you like to conclude?
Sure. Yeah, I also want to say thank you, especially to Stefan, because he did most of the work here for that example, but also to Lubos, because he's the organizer of that webinar. And of course, I also want to thank the audience for spending the time on that webinar. Thank you.
Okay, so thank you all, and this would be really it from us. So okay, we leave you with that, and bye bye for now.